video is about aldehydes and ketones, not surprisingly, as that is what the title is here. And it covers three things. First of all, recognizing and depicting aldehydes and ketones, and then nomenclature of aldehydes and ketones, and finally, reactions of aldehydes and ketones. And it's not necessarily the case that you just watch this one time all the way through, start to finish, and be done. You're perfectly welcome as you're watching this to pause it, rewatch it, look at things again, something you don't understand, go back and go through again. If there's a worksheet that accompanies this video, and so if you want to look at a section of the video and then stop and work on the worksheet, and then move on to the next section and the next section of the worksheet, you're very much welcome to do that. So it is not necessarily the case that you're just supposed to watch this one time through from start to finish and be done. You should use this video in the way that best helps you learn the material and work through the worksheet. And so, as with a lot of presentations around organic chemistry, I like to start by just showing some examples of things. So I've got a couple of things here to start out with. This is the steroid hormone progesterone. It is involved in maintaining female pregnancy. And you can see that it contains not one, but two ketones. Here's one ketone here in what's called the A ring of the steroid. And then another ketone here attached to what's known as the D ring of the steroid. And I've also included an aldehyde. This is cinnamaldehyde. It is the flavor or the odor and flavor and taste of cinnamon. So it is an aldehyde. Okay, well, let's talk about what qualifies a thing to be an aldehyde or a ketone. And back at the beginning of the course, when we were doing the chapter that's just a general review of organic chemistry, I think it's chapter 11, but I'm not 100% sure. We went through a table of functional groups, and aldehydes and ketones fall into that larger group of functional groups that contain a carbonyl. And as you'll recall, a carbonyl is a carbon double bonded to an oxygen. What that leaves the carbon, since carbon always makes 4 bonds, anytime it is double bonded to an oxygen, that leaves it 2 other bonds to make. If one of those bonds is to a alkyl group or an aryl group, and the other bond is to hydrogen, then that is going to be an aldehyde. Whereas if both of those bonds are to R groups, that is alkyl groups or aryl groups, then that's a ketone. And by the way, if both of those bonds are to hydrogen, then that's also an aldehyde. The simplest possible aldehyde is formaldehyde, in which the carbonyl is simply bonded to 2 hydrogens. And as a reminder, that C double bond O is called a carbonyl group. We can depict aldehydes in various ways, and at various times your textbook will depict them various ways. Either in a, and this is all has to do with depicting them as skeletal structures. So I've actually got 4 different ways here of drawing what's known as butanal, or commonly known as butyraldehyde. We can draw the aldehyde, we can indicate the carbon of the carbonyl group and then the hydrogen attached. Or in more common skeletal structure drawing, we simply just don't indicate the carbon, and of course it is implied that it is there. So this is probably the most common way that I would draw an aldehyde, would be like this. Because hydrogens are implied where they are not drawn, but their presence is necessary to have the carbon make 4 bonds, it is possible to draw an aldehyde this way, in which the bond to the hydrogen atom isn't shown. I tend to draw them like this, just to make it explicit that we're talking about an aldehyde. And then finally, a real shorthand way of doing this is just to use CHO as an abbreviation for an aldehyde. So these are all common, these are all acceptable ways of depicting aldehydes. And so whichever way you want to draw them, you should be prepared to see all 4 of these things and realize that you're seeing an aldehyde. What are some examples of aldehydes and ketones? Well, in the very first slide, I showed you progesterone and cinnamaldehyde. This is formaldehyde, which I had mentioned earlier. It's the simplest possible aldehyde in which both of the bonds being made by carbon are to hydrogen atoms. So that qualifies it as an aldehyde, kind of a double aldehyde. This is known colloquially as methylethyl ketone, or MEK. It's used as an industrial solvent. It is also its systematic name, as we'll discuss a little bit later, how to systematically name these, is butanone or 2-butanone. Turns out you don't need to say that. We'll talk about this later. Here is cyclohexanone. And then this is another aldehyde. This is called vanillin. This is the flavor component of vanilla. And this actually contains a lot of functional groups. There's a phenol there, as you can see, an OH attached to an aromatic ring. There is an ether here, a methoxy group attached to the aromatic ring, so a methyl aryl ether. And then there's the aldehyde group here. And because aldehydes take precedence in nomenclature over ethers or alcohols, this would be considered a hydroxyaldehyde. Okay, how do we name aldehydes? Well, there's no such thing as a cyclic aldehyde in which the aldehyde is actually part of the ring. You can have aldehydes that have rings attached to them, either aromatic or non-aromatic, but you cannot have a ring in which the carbonyl group is part of the ring and have that be an aldehyde. Because if you had a ring in which the carbonyl group was part of the ring, that would make it a ketone. So there's no such thing in a sense as cyclic aldehydes, in that the aldehyde group itself is contained in a ring structure. And so there's always going to be a carbon chain of some sort, even if it's just one carbon. And so, for example, this is an aldehyde in which the carbon chain is just one carbon. Here's another aldehyde in which the carbon chain is just one carbon. Back here, I've got an aldehyde in which the carbon chain is 4 carbons. So in naming, I'm going to find the longest carbon chain that contains the carbonyl carbon of the aldehyde. I'm going to simply take the name associated with that chain. So for example, if it's 4 carbons is butane. And so I'm simply going to put the name al on the end. So this becomes butanal. And then we're going to number the chain so that the carbonyl carbon is carbon number 1. And in an aldehyde, the carbonyl carbon is always going to be at the end of the chain. That's what makes it an aldehyde. If it was not at the end of the chain, it would be a ketone. And so therefore, we are always going to number the aldehyde carbon as carbon 1. And so, for example, here is this aldehyde, which has 5 carbons, 1, 2, 3, 4, 5. Therefore, it is called pentanal. So that's a simple example of an aldehyde in which it doesn't have any substituents. It's simply a carbon chain in which we have an aldehyde on the end. Now we can have aldehydes that have substituents. So if I take a look at this molecule, I'm once again going to find the longest carbon chain that contains the carbonyl, the aldehyde carbonyl. 1, 2, 3, 4 carbons there. 1, 2, 3 carbons there. So we're going with the 4 carbons. 4 carbons is butane. Therefore, this is butanal. We never have to indicate what carbon the carbonyl is on, because if it is an aldehyde, it must be at carbon 1. So the root, the parent structure, is butanal. It contains 2 substituents, a bromo and a methyl. And we're once again going to name those in alphabetical order. So the bromine is on carbon 4, 1, 2, 3, 4. The methyl group is on carbon 2. And therefore, this is 4-bromo, 2-methyl-butanal. Here is a aldehyde that contains a ring, but once again, the ring is not part of the aldehyde itself. The carbon chain consists of 2 carbons, 1, 2. And so that carbon number 2 has a phenyl group. As you recall, a benzene ring, when it is a substituent, is referred to as a phenyl group. Therefore, this is 2-phenyl ethanal. 2 carbons, therefore that's ethane. It's an aldehyde, ethanal. therefore 2-phenylethanol. How do we name ketones? Well, we're going to start in the same way and finding the longest carbon chain that contains the carbonyl carbon. Then we're going to replace the E at the end of the parent name with -one. So it was al for aldehydes. For ketones, it is -one. And then we're going to number the chain so that the carbonyl carbon has the lowest possible number. Now, it's generally not going to be, although there are some exceptions that you may run into, but generally the carbonyl carbon can't be at carbon 1, because if it was at carbon 1, it would be an aldehyde. And so, but we do want to number the chain so that the carbonyl carbon of our ketone has the lowest possible number. And so here are some examples. Here is a case of a ketone that has no substituents. And so it's just a carbon chain with a carbonyl on it. And so therefore, we're going to just count the carbons first. 1, 2, 3, 4, 5, 6. So it is hexane. It has a carbonyl. It's not on the end, so it's not an aldehyde. It's a ketone. Therefore, that is hexanone. And then we're going to number it from the left side to the right side, because that puts the carbonyl carbon at the lowest possible position. 1, 2, 3, as opposed to 1, 2, 3, 4. So this is hexanone. This compound, I am going to look for the longest carbon chain that contains the carbonyl carbon. That's going to be 1, 2, 3, 4, 5. I could go 1, 2, 3, 4, but that's only 4 carbons. And so the longest chain that contains the carbonyl is also the longest chain, period. It is 5 carbons. Again, we're going to number this one from the left because it puts the carbonyl carbon at carbon 2, whereas if we numbered from the right, it would put the carbonyl carbon at carbon 4. So it's pentane, pentaneone, 2-pentaneone. Now my 2-pentaneone has 2 substituents on it. Each is a methyl group. Each is attached to carbon 3. 1, 2, 3, 4, 5. Therefore, this is 3,3-dimethyl 2-pentaneone. Here is another straight chain, so there isn't any branching in the carbon chain. So we're simply going to count the number of carbons in the chain. 1, 2, 3, 4, 5, 6, 7. 7 carbons is heptane. It is a ketone because it has a carbonyl, but it's not at the end. So this is heptanone. We're going to number it from the side, not that puts the substituent at the lowest number, but that puts the carbonyl group at the lowest number. So we're going to number from this direction. 1, 2, 3, 4, 5, 6, 7. Because that puts the carbonyl carbon as carbon 3. If we went from this side, 1, 2, 3, 4, 5, the carbonyl carbon will be carbon 5. And so we number from the right. That makes it 3-heptanone. And then we've got a bromine on carbon 7. So this is 7-bromo. 3-heptanone. So if you want to stop this now and do the nomenclature examples on the worksheet, that's great. Otherwise, let's press forward. Naming cyclic ketones. As I mentioned before, you cannot have a cyclic aldehyde in which the aldehyde itself is part of the ring. If you have a carbonyl group in which the carbonyl carbon is part of a ring, that must be a ketone. And so by definition, the carbonyl carbon is going to be carbon 1. And then we're simply going to number it in the direction that gives the substituents the lowest possible combination of numbers. So this is carbon 1. If I number in this direction, the 2 methyl groups are on carbon 3, whereas if I number in this direction, that puts the 2 methyl groups on carbon 5. So this compound is correctly named 3,3-dimethyl cyclohexanone. So cyclohexane is a ring of 6. It's a ketone, so cyclohexanone. And then the methyl groups are both on carbon 3, so it's 3,3-dimethyl cyclohexanone. Here's a 5-membered ring that contains a carbonyl carbon, and so the parent name is going to be cyclopentane. 1, 2, 3, 4, 5, cyclopentane. It's a ketone because one of the carbons is a carbonyl carbon. So it is cyclopentanone. And then I'm going to number it in the direction that puts the ethyl group at the lowest possible number. So this is 2-ethyl cyclopentanone. Well, having talked about nomenclature of aldehydes and ketones, let's go ahead and talk about their reactions. And so both aldehydes and ketones can be reduced by catalytic hydrogenation into primary or secondary alcohols. And the reagent here is the same as the reagent for reducing alkenes or alkynes to alkanes, which is hydrogen on palladium. So before we learned you can reduce a carbon-carbon double bond or a carbon-carbon triple bond to a carbon-carbon single bond. You can also reduce a carbon-oxygen double bond by hydrogenation into a carbon-oxygen single bond. And this is, in fact, simply the reverse reaction of what we learned in the previous chapter on alcohols, which is that you can oxidize a primary alcohol to an aldehyde, and you can oxidize a secondary alcohol to a ketone, and therefore you can reduce a ketone to a secondary alcohol, and you can reduce an aldehyde to a primary alcohol. And so let's take a look at some examples of this. If I take this ketone, which we were naming earlier, this 3,3-dimethylcyclohexanone, and treat this with the hydrogen in the presence of palladium, the carbon-oxygen double bond will be reduced. A hydrogen atom will be added to each position, one to the carbon and one to the oxygen, to give me 3,3-dimethylcyclohexanol. So 3,3-dimethylcyclohexanone reduced to 3,3-dimethylcyclohexanol. And if I take this molecule that is called benzaldehyde, it has a common name, benzaldehyde, and I do and once again, remember that the CHO is depicting an aldehyde. That means there's a C double bond O and then a single bond to an H. I'm going to reduce that carbon-oxygen double bond with hydrogen on palladium. It's going to add one hydrogen to the carbon. It's going to add one hydrogen to the oxygen. I will now get this primary alcohol. Ketones give secondary alcohols, aldehydes give primary alcohols. Well, we can think for a second about reduction and chirality, because if you think about it now, what we're doing is we are taking a carbon that is making a double bond and therefore is only bonded to 3 atoms and therefore cannot be a chiral center. And we are adding a hydrogen atom to it so that it now is making 4 single bonds, one to carbon, one to carbon, one to the hydrogen that's not shown, and one to oxygen. And anytime a carbon is making 4 single bonds, then the possibility exists that it might be a chiral center. And so the possibility exists in these reductions that perhaps we're generating chiral centers. So let's just talk this through. Here is the reduction of benzaldehyde into what is called benzyl alcohol. And I want you to think about what's happening when we reduce an aldehyde. Anytime we reduce an aldehyde, we're making a primary alcohol. And a primary alcohol is an OH that is attached to a CH2 group. Well, you recall that in order for a chirality center to exist, in order for a tetrahedral carbon atom to be a chiral center, the 4 things it's attached to have to be different from each other. But anytime I've got a primary alcohol, 2 of the substituents are hydrogen. Hydrogen here, hydrogen there. And therefore, when I reduce an aldehyde, it does not create a chiral center. It never will. By contrast, when I reduce a ketone, I'm taking a carbon that was bonded to 3 things and making it a carbon that's bonded to 4 things. But now only one of those things is going to be a hydrogen, because previously it was carbon, carbon, and oxygen. Now it's carbon, carbon, oxygen, and hydrogen. And therefore, reducing a ketone may create a chiral center. In this case, it does, because we have 4 different things. We've got an oxygen, we've got a hydrogen, we've got a carbon that when we go around the ring this way does not look the same as this carbon when we go around the ring that way, because in order for them to be the same, there would also have to be 2 methyl groups on this carbon. And therefore, we are, in fact, creating a chiral center when we reduce 3,3-dimethylcyclohexanol. So let's take a look at 3 possible things that could happen. One is the first thing would be when we reduce a ketone, and the carbon, the tetrahedral carbon that we are generating from what was previously a trigonal planar carbon is now becoming a tetrahedral carbon. So the first possibility would be that that is not a chiral center, and that's the case with cyclopentanone. Even though I've shown this as a wedge forward, this is in fact not a chiral compound because the R substituent in this way is the mirror image of the R substituent in this way. You can see that you can draw a plane of symmetry through this molecule. And so this is the first example, a molecule, a ketone that we reduce, which does not create a chiral center. By the way, all the examples I'm giving you here are rings, but it is also possible for this to occur with an acyclic ketone. I can reduce some acyclic ketones that create chiral centers, and I can reduce some acyclic ketones that do not create chiral centers. But for the purpose of this video, I'm just using as examples cyclic ketones. So that's the first type of thing. I'm creating a new tetrahedrocarbon, but it is not a chiral center. Here, if I reduce cyclohexenone, this would be 2-cyclohexenone, I'm sorry, cyclopentenone. I am creating a chiral center because O, H, and then the R group going in this direction is not the mirror image of the R group going in that direction. And therefore, I am creating a chiral center. And therefore, in the process of doing this reduction, I will make two compounds, the two enantiomers. They are mirror images of each other. And so I will create a 50-50 mix of this enantiomer and this enantiomer in my product. There's a third possibility, and then that would be a molecule that a ketone, whether cyclic or not, that already contains a chiral center. So here is 3-methylcyclohexanone, but it's only a single enantiomer of 3-methylcyclohexanone. It has the wedge forward. Now when I do the reduction, I am creating a new chiral center because I am making a tetrahedral carbon. It's got oxygen attached to it. It's got hydrogen attached to it. It's got an R group that does not look the same way, that going this direction is not the mirror image of the R group going in that direction. And therefore, I am creating a chiral center, but it already contains a chiral center. So here's something important to notice. The reduction does not alter this existing chiral center at all. It's going to retain the same configuration that it had before. But the new chiral center that I'm creating it could be reduced so that the OH winds up being face up, or it can be reduced so that the OH winds up pointing down. And so I'm creating two new compounds which have different configurations at the tetrahedral carbon I created, but retain the same configuration at the chiral center that already existed. Okay, well, there's a series of reduction reactions in your worksheet, and so if you wanted to stop and work on reductions, you're perfectly welcome to do so at this point. Otherwise, we'll carry on. The other thing we can do is, when it comes to carbonyl compounds, is oxidation. But the only one of these that we can oxidize is an aldehyde. Because a ketone, in order to oxidize a ketone, in order to oxidize a carbonyl, oxidation of a carbonyl involves insertion of an oxygen into a CH bond. Well, in a ketone, there aren't any CH bonds, and therefore we can't CH bonds that are part of the ketone functional group itself. So we cannot oxidize a ketone, but we can oxidize an aldehyde to a carboxylic acid, and the reagent that we use for this is potassium dichromate. We learned back in the chapter on alcohols that we can take an alcohol and oxidize it with dichromate to an aldehyde, which then further goes on and can't be isolated and is oxidized to the carboxylic acid. And so this is simply just starting halfway. Instead of starting with the alcohol and oxidizing it to a carboxylic acid, we're starting with the midpoint, which is the aldehyde, and oxidizing it to a carboxylic acid. Okay, that is actually everything that I have to say on this video, so feel free to try the worksheet if you haven't already. And as I mentioned before, this video is all about being watched as many times and as at whatever pace is necessary to be able to understand the material and get the work done. Thanks so much for watching.